recording something and all and. Welcome students. Welcome to St. Joseph's open web-based learning platform. So we learn for a soulful and enriching e-learning experience. Welcome to Department of Mathematics. Our topic name is Differential Equations. Instructor for this chapter B. Bharati, MSc, Mathematics, Assistant Professor, Department of Mathematics, St. Joseph's College for Women, Autonomous, Vishakhapatnam. Learning outcomes. By the end of this chapter, students able to classify the differential equation with respect to the order and linearity. Able to explain the meaning of a solution of a differential equation. Able to solve first order ordinary differential equation. Student will have a working knowledge of basic application problems. Let's see the content. Introduction, definition of differential equation, types of differential equations, order of the differential equation, degree of the differential equation, related examples on order and degree of the differential equation, linear differential equation, working rule to solve linear differential equation, and related examples. Today I would like to discuss with you differential equations. Before that, I would like to give an introduction to differential equations. Let us first understand what are differential equations. An equation that contains the derivative of an unknown function is called a differential equations. Differential equations are mainly used in the fields of biology, physics, engineering, and many other fields. Before going to start the topic, I want to recall the previous knowledge. What is an equation? An equation is a mathematical statement that asserts the equality of two expressions. It consists of two sides separated by an equal sign. Each side of the equation can contain numbers, variables, and operations. Equations are fundamental in mathematics because they represent relationship between quantities and are used to solve for unknown values. Come back to our topic, differential equations. In general, definition of differential equation is nothing but a differential equation is an equation which contains the derivatives of one dependent variable with respect to the other independent variable. See, there are some examples here. The first one is dy by dx is equals to sin x. Second one is second derivative of y with respect to x. So d square y by dx square plus k square y in k square into y is equals to 0. Third one is dy by dx is equals to f of x comma y. These three are the examples of the differential equations. If you look into these three examples, here y represent or acts as a dependent variable and x is independent variable. Now we are going to learn different types of differential equations. There are two types of differential equations. One is ordinary differential equation, the other one is partial differential equations. Whereas in this slide, let us see what is an ordinary differential equation. An ordinary differential equation involves function and its derivative. It contains only one independent variable and one or more its derivative with respect to the variable. What I mean to say is that if we have a function like y is equals to f of x, here y is dependent variable and x acts as independent variable. If you do derivative, we can write dy by dx. Here y is dependent variable with respect to the only one independent variable x. See, there are some examples. Dy by dx plus d square y by dx square plus y square plus 2x is equals to 0. Second one is d square y by dx square plus e to the power of 2x into y is equals to 0. In these two examples, we are going to notice one thing, that is here y acts as a dependent variable with respect to the only one independent variable, say x. In this slide, let us see what is partial differential equation. Partial differential equation, commonly known as PDE, is a differential equation containing partial derivatives of the dependent variable with more than one independent variable. What I mean to say is that an equation containing one or more partial derivatives of an unknown function of u or more independent variables is called a partial differential equations. Clearly we can see in this example. See, if you look into this example, there are two partial derivatives. One is dou by dou t, the other one is dou square by dou x square, and one unknown function, that is u. And here more than, we have to cross check, more than one independent variable, no? So if you look into this example, there are two independent variables, say x and t. In this slide, we are going to learn the order of the differential equation. What is order of the differential equation is nothing but order of the differential equation is the order of the highest derivative present in the equation. That means highest derivative of a given function treated as an order of a given differential equation. There are some examples. First one is d cube y by dx cube plus x into dy by dx minus 4xy is equals to 0. In this equation, the order of the highest derivative is 3. Hence, this is a third order differential equation. If you look into the second example, dy by dx plus d square y by dx square plus 2x is equals to 0. Order of the highest derivative is 2. Hence, this equation represents a second order differential equation. We already discussed what is an order of the differential equation. Now, in this slide, let's see the degree of the differential equation. The degree of the differential equation is represented by the power of the highest order derivative in the given differential equation. That means power of highest order derivative appearing in differential equation when written as a polynomial in differential equation. Whenever we want to find degree of the differential equation, we have to follow two things. First one is to find out highest order derivative, then look into the power of the highest order derivative. See, there are some examples. First one, 7 of d power y, d power 4y by dx power 4 plus 5 into d square y by dx square whole power 4 plus 9 into dy by dx whole power 8 plus 11 into y is equals to 0. This is differential equation is of fourth order under degree 1. Second example, dy by dx whole square plus dy by dx minus cos cube x is equals to 0. This is differential equation of first order and of second degree. Third one, d square y by dx square whole power 1 by 2 plus x into dy by dx whole cube is equals to 0. This differential equation is of second order and the first degree. In this slide, we are going to see related example. Our question is y is equals to x into dy by dx plus root over 1 plus dy by dx whole square. In order to find the degree and order of the given differential equation, we want to simplify the given question. For that, bring x into dy by dx to the left side part. So y minus, then it becomes y minus x into dy by dx is equals to root over 1 plus dy by dx whole square. Next, in order to simplify, squaring on both sides. 1 minus x into dy by dx whole square is equals to 1 plus dy by dx whole square. As we all know the formula of a minus b whole square, right? A square plus b square minus 2ab. A square is nothing but y square plus b square is nothing but x square into d square y by dx square minus 2ab. 2 into a into b is nothing but y into x into dy by dx, which is equals to 1 plus dy by dx whole square. So look into this equation, we clearly say that order is 2 and the degree is 1. Let us see linear differential equation. In general, what is linear differential equation? A first order differential equation is called a linear equation. Look into the definition here. A linear first order equation is an equation that can be expressed in this form. A1 of x into dy by dx plus a0 of x into y is equals to b of x. Here we used three constants, say a1 of x, a0 of x and b of x. These three constants depends only on one independent variable x but not on y. In order to reduce into the standard form of the linear differential equation, we are going to divide it by a1 of x in equation 1. We can, after dividing a1 of x throughout this equation, we can rewrite equation 1 in the standard form. That is, dy by dx plus p of x into y is equals to q of x. As we already know that here y is dependent variable with respect to x and here x is the only one independent variable and here p of x and q of x, these two are the continuous functions on an interval. See, working rule to solve the solution for linear differential equation. In order to find a solution for any linear differential equation, first step we need to convert given equation into standard form. Here the standard form is dy by dx plus p of x into y is equals to q of x. We already know that here y is dependent variable with respect to x and here x is independent variable. P of x and q of x, these two are continuous functions. Next step, to calculate the value of integrating factor by using this formula, that is mu of x is equals to exponential to the power of p of x into dx. After got integrating factor, we have to multiply throughout inequality by mu of x or integrating factor. Last step we need to do integrating on both the sides. Then we get required solution for the given differential equation. Let us solve given differential equation. 1 plus x square into dy by dx plus 2xy minus 4x square is equals to 0. First write down given equation as it is. That is, given that 1 plus x square into dy by dx plus 2xy minus 4x square is equals to 0. As we discussed in the previous slide, first step we need to convert given equation into standard form. For that, first send minus 4x square to right side part. That is 1 plus x square into dy by dx plus 2xy is equals to 4x square. Next move on to the next slide. Here divided by 1 plus x square throughout the inequality. Then equation 1 becomes dy by dx plus 2x by 1 plus x square into y is equals to 4x square by 1 plus x square and let it be equation 1. Here equation 1 is in the form of linear differential equation. Next thing we need to find out integrating factor to solve general solution for the given differential equation. As we know, integrating factor formula is e to the power of integral p of x into dx. We're going to start this slide. In previous slide, we are started to prove integrating factor. Formula of integrating factor is e to the power of integral p of x into dx. If you compare equation 1 to the standard form, then we got the values of p of x and q of x. Here p of x is nothing but 2x by 1 plus x square. So that is how we got e to the power of integral. Instead of p of x, here we replace the value of p of x, that is 2x by 1 plus x square into dx. Move on to the next line, which is equals to e to the power of log of 1 plus x square. How we written directly log of 1 plus x square means we have a formula, that is integral f dash of x by f of x is equals to log f of x. If you look into this integral part, here f dash of x by f of x means here f of x value is 1 plus x square. If you do derivative for the denominator part, it becomes 2x. Now this whole integral part looks like integral f dash of x by f of x. Formula is log f of x. So that's how we written e to the power of, instead of that whole integral part, using that formula we written log of 1 plus x square. Next line, by using anti-logarithm, we directly return 1 plus x square. Next, and let that value be equation 2. General solution, we need to find general solution of equation 1. Formula is y into integrating factor is equals to integral q into integrating factor ds. But in place of q, we directly substitute value of q, that is 4x square by 1 plus x square. Move on to the next line, y into, we already got integrating factor value in equation 2, no? Now directly substitute that integrating factor value in this line. So y into, instead of integrating factor, we got 1 plus x square, which is equals to integral 4x square by 1 plus x square into, again integrating factor is nothing but 1 plus x square into dx. That means wherever we have integrating factor, replace with the value of integrating factor. Next line, y into 1 plus x square, which is equals to integral, in the above line 1 plus x square 1 plus x square get cancelled. Left over part is integral 4x square into dx. Finally, therefore y into 1 plus x square is equals to, here 4 we treated as a constant, so take outside, 4 into integral x square into dx. Integral x square value is x cube by 3 plus c. Let us solve example 2. Given question is solve cos square x into dy by dx plus y is equals to tan x. Solution is given that dy by dx plus y by cos square x is equals to tan x by cos square x. How did we get this? Means throughout inequality divided by cos square x. After dividing cos square x to the given equation, we got dy by dx plus y by cos square x is equals to tan x by cos square x. Move on to the next line. Dy by dx plus 1 by cos square x formula is secant square x. So it can be written as secant square x into y is equals to tan x into, as I told you 1 by cos square x value is secant square x. Let it be equation 1. Now equation 1 is in the form of linear differential equation. Next we need to find integrating factor to find general solution. So integrating factor formula is e to the power of integral p of x into dx. Instead of p of x, we took secant square x. No. How did we written secant square x? Means if you look into the equation 1, instead of p of x and q of x, we got the values, that is secant square x as p of x and q of x is nothing but tan x into secant square x when you compared given equation to the standard form. And move on to the next line, e to the power of tan x. Have we directly written secant square integral secant square x into dx is tan x, means we have a since part for that line. If you look into the since part, d by dx tan x value is equals to secant square x. If you substitute secant square x into the integrating factor formula, their integrating derivative cancel and leftover part is tan x. So we return e to the power of tan x. Solution of equation 1 is y into integrating factor is equals to integral q into integrating factor dx. But in place of q, we directly substitute q value, that is tan x into secant square x. Move on to the next line. Y into, substitute integrating factor in the above line, y into e to the power of tan x is equals to integral tan x into secant square x into, instead of integrating factor we got value is e to the power of tan x into dx. Here we return the same step which is there in the previous slide, that is y into e to the power of tan x is equals to integral tan x into secant square x into e to the power of tan x into dx. We are going to give a name for the tan x in the next line, so that let tan x is equals to t. Do derivative on both the sides. Tan x derivative is secant square x into dx, which is equals to dt. And substitute this secant square x into dx value and tan x value in the above value. Y into e to the power of tan x is equals to integral. We already took tan x as t, no? So integral, instead of tan x replace with t, and secant square x into dx becomes dt, and e power tan x becomes e power t. Finally we got integral t into e power t into dt. That is how we got equation 2. Next, apply integral uv formula. Integral u into v dx formula is u into integral v into dx minus integral u dash into integral v of x into whole dx. So apply same formula for equation 2. Take integral t into e power t into dt. Choose u as t and v as e power t. Apply this formula for equation 2. So t into integral e power t into dt minus integral u dash means t dash, integral v into dx means e power t into dt whole dt. Next line, t as it is, integral part of e power t again e power t minus integral derivative of t is nothing but 1 with respect to t. So 1 into integral e power t, again it becomes e power t. So finally after calculating right side part, integral e power t into dt we got. So we got t into e power t minus e power t plus c. Equating left and right hand side, integral t into e power t into dt is equals to, take e power t as common, e power t into t minus 1 plus c. Now substitute this value in a above equation 2. Write down equation 2 left side part as it is, y into e to the power of tan x, which is equals to, in equation 2 instead of right side part we got a value is e to the power of t into t minus 1 plus c, no? Again replace t as tan x value. Then we got e to the power of tan x into tan x minus 1 plus c. Therefore, in the next line, we are going to divide it by e power tan x throughout the inequality. Then we got y is equals to tan x minus 1 plus c into e to the power of minus tan x. How did we get this step? Means throughout inequality we are dividing by e to the power of tan x. Left side part e to the power of tan x and e to the power of tan x get cancelled. The right side part e power tan x cancel, and c by e to the power of tan x, no? When denominator part brings to the numerator part, then it becomes e to the power of minus tan x. So that is how we got y is equals to tan x minus 1 plus c into e to the power of minus tan x. Thank you all for sparing your valuable time.